Okay, well, in this lesson, we're going to be discussing the other term or the remainder of the Taylor polynomial of order n, which is the error obtained by approximating a function by a Taylor polynomial. However, in a previous lesson, we have introduced Taylor and Maclaurin theories. We have seen how we could determine the expansion corresponding to Taylor and Maclaurin series that represent given functions, and we have seen how we could determine the radius and interval of convergence. Now, in this lesson, we're going to be focusing on the other term, and we're going to later on discuss the Lagrange form of this other term. So if I were to start first by recalling what a Taylor polynomial of order n is, that is centered at A. So the Taylor polynomial is in fact a polynomial of degree n centered at A, which means that it is the sum of the terms that start from k equals to 0 to n of the terms defined by x minus a to the k, multiplying the Taylor coefficient, which is given by the derivative of order k at A divided by k factorial. However, the Taylor series would in fact be the limit of the Taylor polynomial as n goes to infinity. Now, the Taylor polynomial of order n would in fact stop at the term of degree n. However, the Taylor series is more like a Taylor polynomial with an infinite degree. So it's the Taylor polynomial of degree n where n goes to infinity. However, if we consider a function f here, which should be continuous and differentiable, because eventually at some point we're going to need to find at least n plus 1 derivatives of f. So the error that we obtain by approximating f of x by the nth partial sum. Now the nth partial sum would be represented by the Taylor polynomial of order n. So by approximating f of x by the Taylor polynomial of order n, the error obtained would in fact be the difference between the function and the Taylor polynomial. So the difference between the function and the Taylor polynomial would actually give us the error of the approximation, which we denote here by Rn of x. So over here, Rn of x is also called the remainder of the Taylor polynomial of order n. So the remainder of the Taylor polynomial is in fact the other term. So over here, the remainder of the Taylor polynomial of order n would in fact be f of x minus Tn of x, which is Taylor polynomial of order n. So the Taylor polynomial would be the difference between f of x and the other term. So Tn of x would be f of x minus Rn of x. Now, taking both sides to infinity, so approaching n to infinity on both sides. On the left-hand side, the limit of the Taylor polynomial as n goes to infinity would in fact be the Taylor series. And on the right-hand side, we have the limit as n goes to infinity of f of x minus Rn of x. However, f of x here is considered to be a constant with respect to the variable of the limit. Now, the variable of the limit is n, and as n goes to infinity, f of x being independent from n would in fact remain f of x. So that would give me f of x minus the limit when n goes to infinity of Rn of x. However, the Taylor series would in fact be a good approximation of f of x when the limit of Rn of x is 0 as n goes to positive infinity. So if Rn of x has a limit of 0, in that case the Taylor series would be a good approximation of the function given. So over here in this theorem, we're going to summarize everything we have said so far. So by considering a function to be t n of x plus r n of x, where t n of x is the nth order Taylor polynomial, of course here centered at a, and Rn of x is the remainder of the nth order Taylor polynomial. So Rn of x would be the error term. So if the limit when n goes to infinity of Rn of x is 0 for x in a minus r, a plus r, then in that case f of x would be well approximated by that Taylor polynomial over that interval. And I remind you that r is the radius of convergence, while I, if I were to call this interval I is the interval of convergence. So f of x would be well approximated by the Taylor polynomial over that interval. Now, if we move to Taylor's formula, or the Lagrange form of the error term given by this approximation. So in order for the Lagrange form to hold, f needs to be differentiable at least till the n plus 1 order. So if f admits n plus 1 derivatives over the interval of conversion, the a minus r, a plus r, then there exists t in xa or t in ax such that. Now, before we discuss the Lagrange form of the error term, let's just discuss a little here the conditions on t. So over here we have introduced a new variable t between a and x. Now, you know for a fact that the interval of convergence is centered at a, and x being an element of this interval, in that case x would either be between a and a plus r, or between a minus r and a. So x has to be on the left or on the right side of a. So depending on the choice of x, or depending on the value of x would be working with, in that case, t would be a value between a and x. So if x is on this side of a, if it's on the left side of a, then t would be between x and a. If x is greater than a, in that case, t would be between a and x. However, keep in mind that either ways, t is just a real number that we're considering between a and x. So going back to Taylor's formula, or the Lagrange form of the error term. So if I have f to admit at least n plus 1 derivatives over the interval of convergence, then there exists a real number t between a and x such that Rn of x would be the derivative of order n plus 1 of t over n plus 1 factorial into x minus a to the n plus 1. Now, you'd notice that the form of this term here would remind you a lot of the terms in the expansion of the Taylor polynomial. So going back to the definition of the Taylor polynomial, you'd notice that you'd have the Taylor coefficient, which is the derivative of order k of a over k factorial into x minus a to the k. Now, the last term of the Taylor polynomial would be for k equal to n. So that would be x minus a to the n multiplied by derivative of order n of f of a over k factorial. However, the Lagrange form uses the n plus 1 term. So the error, in fact, obtained by this approximation would more or less be as if we're considering the next term in the expansion, the one that follows the last term in the polynomial, the one corresponding to k equals to n plus 1, of course, where the Taylor coefficient is evaluated at t instead of x. Now, we're going to justify a little this form of the other term. However, we're not going to be given like the true mathematical proof of the Lagrange form, but we will be justifying it mathematically, more or less. So in fact, over here, if we start by the Taylor polynomial of order n, so we have Tn of x to be f of a plus f prime of a into x minus a. Now over here, the first term is f of a because when k is equals to 0, the derivative of order 0 is the function itself. Now for k equal to 1, we'd actually have the first derivative times x minus a over 1 factorial. Now the second one, the second derivative, or in fact the third term, is the second derivative into x minus a all squared divided by 2 factorial, all the way to the nth term, which is the derivative of order n of a. So that's the derivative of order n of a into x minus a to the n over n factorial. Now over here, if we consider the function f of x, which we aim to approximate by the Taylor polynomial of order n over the interval of convergence, which is a minus r, a plus r. So what is really happening here? So if I were to do just like a small sketch. Now if this is a minus r and a plus r, the interval of convergence. Now a would in fact be the center of that interval. So if I were to draw the function f representing, or the curve representing the function f over that interval, we're only interested in that interval. Now over here, you'd notice that when x is a, Tn of a, all these terms would in fact be 0 when x is a. So we would have Tn of a to be equals to f of a. So the curve corresponding to the Taylor polynomial would intersect the curve corresponding to the function f at x equals to k. However, the other term is determined by studying how far it shifts, the curve of f shifts away from the Taylor polynomial as it goes further from x equals to a. So over here we can see this as if this is the curve corresponding to t of n, and the other term would be representing the difference, that area or that region between them. So the difference between the actual curve of the function and the curve of the Taylor polynomial. So over here, Rn of x. So Rn of x we have seen is in fact f of x minus Tn of x. Now let's just study the value of the remainder or the other term at a, and as well as its derivative at x equals to a, exactly, because these we will need later on. So over here, if I were to have, let me just rewrite that, the derivative, or in fact the other term Rn of x is f of x minus Tn of x. Now at x equals to a, I'm going to write these in red to differentiate them from the rest of the proof. So Rn of a is f of a minus Tn of a. And we've just seen that Tn of a is in fact f of a. So that difference is 0. Now the derivative of order n of a would be the derivative of f at a minus the derivative of the Taylor polynomial at a. Now going back to the expansion of the Taylor polynomial, now you'd notice as I consider the first derivative, Now, this term being zero, this term being constant, its derivative is zero. However, this first term would have a derivative of f prime of a. Now, that is in the form of a linear polynomial where the coefficient of x is f prime of a. So the derivative of this term would in fact be f prime of a. However, for the rest of the terms, by just dropping the coefficient and by dropping the exponent and subtracting 1 from the exponent using the power rule of the derivative, in that case, the remaining terms would still have an x minus a. So when x is equals to a, all of them would be zeros. So we're left with t prime of a equals to f prime of a. So you notice that difference is also 0. And similarly, the derivative of order k of a is the derivative of order k of f at a minus the derivative of order k of the Taylor polynomial at a. And over here, the derivative of order k of t would in fact be at a, would in fact be equals to the derivative of order k of f. So that difference is 0. So you'd notice that at x equals to a, the derivative of r n of x is equals to 0 at x equals to k. So we're going to just keep this aside until we're going to need it later in the proof. So now going back to the fact that Rn of x is f of x minus Tn of x. So going back to the fact that Rn of x is f of x minus Tn of x. Now we're working for all x in the interval of convergence. We're no longer working at x equals to a. Now, if I find the derivative of each term in this expression all the way to the n plus 1 derivative. Now, why is it so? It's because the Lagrange form of the error term includes the derivative of order n plus 1 of f. So I need to differentiate this all the way to the derivative of order n plus 1. Now over here, as I differentiate, I'd have the derivative of order n plus 1 of r equals to the derivative of order n plus 1 of f at x minus the derivative of order n plus 1 of the Taylor polynomial of order n. Now by looking at this term, now the last term, the derivative of order n plus 1 of the Taylor polynomial. Now the Taylor polynomial here is of order n. So if I differentiate a polynomial to the nth order, n plus 1 times, in that case the derivative would be 0. So it's as if we're looking at a polynomial of degree 2 that I differentiate 3 times all the way to f triple prime. So all the way to the third derivative, starting from the third derivative, the derivative of the polynomial will be equals to 0. So over here I have the Taylor polynomial, which is of order n, so which is of degree n, that I differentiated n plus 1 times, so that derivative is in fact 0. So now we'd be left with Rn, of course the n plus 1 derivative of Rn is equal to the derivative of order n plus 1 of f. Now, why is this in fact useful of obtaining the derivative of order n plus 1 of r equal to the derivative of order n plus 1 of f? Because since over here we're working over a finite interval, so we're working over the interval of convergence that would go from a minus r to a plus r. However, as we've seen before, x could either be between a and a plus r, and between a minus r and a. So over here, what I'm interested in is just the interval over which is just the interval between a and x, whether x is on the right side or the left side of a. Let's just consider it on this side for the moment. Okay, so since x is between a minus r and a plus r, then just by considering that interval would have a maximum of an interval of convergence. So the maximum size of that interval between a and x would actually be the interval of convergence, considering that x could be on this side or on that side. So I'm going, for the time being, be focusing on the interval between a and x. Because as you know, sometimes r could be infinite, and the interval of convergence would be all r, would be the set of r real numbers. So the reasoning we're about to take will not be valid over infinite intervals. So this is why I need to be working over a finite interval. And however, the values of x that the polynomial take in order to approximate the function will eventually be finite. So it's enough to be just working between a and x. Now, working between a and x, that is a finite interval. So over here, the derivative of order n plus 1 of f can actually be bounded. So let me just over here just do a small sketch again. So now we're working between a and x, and suppose that the derivative of order n does have this shape. So this is the representing the derivative of order n plus 1 of f over the interval a x. Now you can actually see that since the interval is finite and the function being continuous, then the function is bounded. It does have a maximum value and a minimum value. But however, over here, I'm only interested in bounding the absolute value of the derivative of order n plus 1. And that is for a reason that because, for example, if the maximum is at y equals to 5 and the minimum is at y equals to a negative 10, in that case, the error between, or the distance separating the x-axis from the minimum would in fact be larger than the distance separating the x-axis from the maximum. So at the minimum of the curve, the error would be bigger. However, by considering the absolute value, if the maximum is 5 and the minimum is negative 10, in that case, the absolute value of the function would be bounded between 0 and 10. So I'd be able to point out easily where distances are larger. And over here, since I'm interested in determining the error term of obtained by approximating a function by a Taylor polynomial. So I'm just interested in the distance between the function and the Taylor polynomial, between the curves of the function and the Taylor polynomial. So I'm just interested in knowing how further the Taylor polynomial is from the actual curve of the function. So that is why here we consider the absolute value of the derivative of order n plus 1 of x to be bounded, or to be smaller than the value of the maximum of the curve over that interval. So now going back to our error term, we have that the derivative of order n plus 1 of r of x to be equal to the derivative of order n plus 1 of f of x. So over here, having the derivative of order n plus 1 of f, we know that it in fact is in fact equals to the remainder of the Taylor polynomial, or sorry, the derivative of the remainder of the Taylor polynomial of order n plus 1. So we can just make the substitution. So over here, in this case, having the absolute value of the derivative of order n plus 1 of r of x to be smaller than m, then in this case, we could integrate both sides between a and x. So over here, I'd have that the integral between a and x of the absolute value of the derivative of order n plus 1 of x dx would be, I'm sorry, I need to change the variable here since I took the bounds from a to x, so I need this to be of t dt, smaller than the integral between a and x of m times dt. And that is for t in the interval ax. Now the integral on the right-hand side of the inequality is easy to determine. However, looking at the integral on the left-hand side, I have the integral of the absolute value of the derivative of order n plus 1 of r. However, we do have this property that would that actually state that the absolute value of the integral is smaller than the integral of the absolute value. So over here, the absolute value of the integral from a to x of the derivative of order n plus 1 of t dt is smaller than the integral of the absolute value of that function. So over here, if a is smaller than b and b is smaller than c, then a is smaller than c. So over here, I could in fact be working with this integral, because I could easily integrate inside the absolute value here. So over here, that would leave me with the absolute value of, now the integral from a to x of the derivative of order n plus 1. Now the derivative of order n plus 1 of r would in fact be integrated into the derivative of order n. So over here, that would give me the derivative of order n of Rn of t between a and x. Of course, that is an absolute value smaller than, now the antiderivative here is m times t between a and x. Now applying the bounds, that would give me, now upper bound minus lower bound, the derivative of order n of x minus the derivative of order n of a. However, we have seen here that the derivative of any order of r at a is in fact equals to 0. So we just drop down the lower term, which is smaller than m into x minus a. However, repeating the same process. Now, repeating the same process n plus 1 times until we eventually reach the remainder or the error function itself, r, would in fact lead us to. So if we were to just do it one more time, I have that the absolute value of the derivative of order n of x is smaller than m into x minus a. So if I were to integrate again, so over here, the integral, again, the integral of the absolute value is in fact greater than the absolute value of the integral. So we can have here on this side the absolute value of the integral. So this is the one I'm going to consider here. So the integral between a and x, so that is the absolute value of the derivative of order n of x. Sorry, that should be t dt is smaller than the integral between a and x of mx minus 1 dt. it should be t again. I'm sorry, I keep messing up with variables. Since I took x at the bound, I need to change the variable inside. However, over here, integrating the derivative of order n, that would give me the derivative of order n minus 1 of the error term. And that is between a and x, and of course inside the absolute value. Now integrating here, now that would give me m into t minus a squared over 2, and that is between a and x. Now applying the bounds, that would give me the derivative of n minus 1 of r at x minus the derivative of order 1 at a, the derivative of order n minus 1 at a, which is in fact 0. That is its absolute value smaller than m into x minus a all squared divided by 2. And for t equals to a, that would be a minus a, which is 0. So repeating that process until we eventually reach r on the left-hand side, we would eventually get the absolute value of Rn of x is smaller than m into x minus a to the n plus 1 over n plus 1 factorial. And that is because we integrated it. We integrated n plus 1 times. Now over here, just to make sense of the factorial at the denominator, it's because when you integrate here again, you would have a cubed over 3. So that would leave you with 2 times 3, which is 3 factorial. Integrate again, that would take x minus a to the power of 4 divided by 2 times 3 times 4, which is 4 factorial. So integrating up to the term to the power of n plus 1, that would leave you with n plus 1 factorial at the denominator. So over here you can actually see that I ended up having the remainder of the approximation in absolute value to be smaller than m into x minus a to the n plus 1 over n plus 1 factorial. So we're getting closer to the Lagrange form here. So over here, just going back to what m is. Now going back to what m is, we know that m is in fact the maximum of the absolute value of the derivative of order n plus 1 of f. So we know that the absolute value of the derivative of order n plus 1 of x to be smaller than f, and that is over the interval ax. So the absolute value of the function being smaller than m, in that case, I know that there exists a value of t in the interval ax for which the derivative of order n of f at t is the minimum over that interval. I'm just going to sketch it here in order for you to see it better. So if I know, for example, if this is the curve representing the absolute value of the derivative of order n plus 1. Okay, so that is the absolute value of the function. It should be positive. It's all above the x-axis. So that is the value of m representing the maximum of that function. So we know for a fact here that since this curve is all above the x-axis and bounded by m, in that case there exists a value of t over the interval ax for which the image of t by this function is minimum. Now it could be on the x-axis, it could be 0. However, it could be different than 0. And the curve, the absolute value of the derivative of order n plus 1 in fact would be 0 if the remainder is 0, if the error if the approximation error is 0, which is very unlikely since we're approximating values here. So there exists a value of t between a and x for which the image by this function over this interval is minimum. So then we can say that there exists t in ax, or we can say in xa, depending on a, whether it's greater than a or smaller than a, okay, such that the derivative of order n plus 1 of t is minimum. In this case, the error, in fact, would be minimum. And that is because this value is, in fact, the smallest possible value that m can take. So for m equals to the absolute value of the derivative of n plus 1 of f at t, in that case, the right-hand side of this inequality is minimum. So over here, in that case, then Rn of x is minimum. Let me just write that, is minimum for Rn of x equals to the derivative of order n plus 1 of t over n plus 1 factorial times x minus a to the n plus 1. And of course, that is for t between a and x. So, of course, over here, we were just more or less justifying the Lagrange form. The real mathematical proof has a lot of more mathematical details in it, so we're not going to go through that. We're just interested in just justifying the Lagrange form. However, in the exercises, you are more likely going to be using the Lagrange form of the error term immediately and not, of course, have to justify it every single time you need to use it. So over here, if we just wrap up using this example, we need to find the Maclaurin series that is generated by the function f of x equals to e to the x and prove that it represents the function f for all x in R. However, regarding the Maclaurin series that is generated by y equals to e to the x, we have found it in a previous lesson. So you could just refer to that lesson that introduced Taylor and Maclaurin series that represent functions in order to remember how we really find the series generated by these functions. So for this example, I am just interested more in showing you how to study the error term. So I'm going to start with the Maclaurin series given. So if you need to recall how this Maclaurin series was determined, just refer back to our previous lesson. So over here we have f of x to be equals to the sum when k goes from 0 to infinity of x to the k over k factorial. Now that is the Maclaurin series that is generated by y equals to e to the x. So I need to prove that this Maclaurin series approximates well y equals to e to the x for all x in R. So first what I need to do is determine the interval of convergence of this series to check over which interval the function is approximated by this Maclaurin series, and then I need to determine the other term that is generated by this approximation and check if the limit of that other term is 0, going back to this theorem. So by determining the interval of convergence, I then determine the limit of the other term. If the limit of the other term when n goes to positive infinity is 0, then f of x is well represented by that series over that interval. So I need to first start by finding r. So over here, if I just call u of n to be the sequence defined by x to the n over n factorial. Of course, such series, we can determine the radius of convergence by just using the ratio test. So I start by determining the limit when n is approaching a positive infinity of the absolute value of un plus 1 over un, which is the limit when n is approaching positive infinity of. Now that's x to the n plus 1 over n plus 1 factorial. Now divided by un, that would multiply this by n factorial over x to the n. So L would in fact be equals to the limit when n is approaching positive infinity of. Now simplifying, that would leave me with an x at the numerator and with an n plus 1 at the denominator. Now keep in mind that x is constant with respect to the variable of the limit, since the variable of the limit is n. So when n goes to infinity, that would be as if I have a constant divided by infinity. So a constant divided by infinity is 0. So whenever the limit is 0, it means that the radius of convergence is actually infinity. So the radius of convergence being infinite, it means that then f of x is equals to this Maclaurin series, or is approximately equals to the Maclaurin series for all x in R. So I know for a fact that I'm working here over all R. So I still need to determine the Lagrange remainder, the Lagrange form of the other term, to be precise, and then consider its limit at infinity. So considering Rn of x. Rn of x is in fact if you want the n plus 1 term. So that would be the derivative of order n plus 1 of t over n plus 1 factorial times x to the n plus 1. Of course, over here, the Maclaurin series is a Taylor series centered at 0. So over here, we know that f of x is e to the x. And the derivative of any order of e to the x is e to the x. So Rn of x would be equals to e to the t over n plus 1 factorial times x to the n plus 1. So what do we know about t here? We know that t is between 0 and x. Over here, keep in mind that this is a Maclaurin series, so it's centered at 0, so a is 0. So t is between 0 and x, which means that e to the t is between 1 and e to the x, which means that e to the t is smaller than e to the x for all x. So over here, I can say that Rn of x is smaller than e to the x times x to the n plus 1 over n plus 1 factorial. So considering the limit when n is approaching positive infinity of Rn of x, so that is smaller than the limit when n is approaching positive infinity of e to the x times x to the n plus 1 over n plus 1 factorial. So over here, taking n to infinity. Now e to the x is constant with respect to the variable of the limit. And over here, x to the n plus 1 divided by n plus 1 factorial. Now, we know for a fact that this is infinity over infinity, it's indeterminate. However, the denominator, if it were to be expanded, it would in fact, the term with the highest degree would in fact be n to the power of n plus 1. So n to the power of n plus 1 goes to infinity way quicker than a constant to the n plus 1, because x here is considered to be constant with respect to the variable. So you could in fact calculate the limit or determine it using your GDC, but in fact that is 0. So I do have that the limit when n is approaching positive infinity of Rn to the x is smaller or equals to 0. However, you'd notice here that e to the t is between 1 and e to the x. So e to the t being between 1 and e to the x, it means that r of n is positive. So r of n being positive, I'm just going to be finishing it here. So r n of x in this case, for this function being strictly positive, so then we can say that the limit when n is approaching positive infinity of Rn of x to be equals to 0. So having the remainder of the Taylor polynomial, or the other term, having a limit at infinity equals to 0, it means that over R, since the interval of convergence is all R, so over R, f of x is well approximated by this Maclaurin series. So that is it for this lesson. In our following lesson, we're going to be discussing some useful mathematical applications of Taylor and Maclaurin series, such as determining or calculating limits and approximating solutions of differential equations, in addition to approximating functions at specific values.